Okay, welcome back, everybody. I hope you've all got your brains in good working order for this next session. It's my pleasure now to introduce shortly Marcos Lopez de Prado, who is the Professor of Practice at Cornell University's College of Engineering and Global Head of Quantitative Research and Development at the Abu Dhabi Investment Authority, or ADIA. That's quite the combination, and we're very lucky to hear from him today. Marcos's groundbreaking work on machine learning and statistical inference methods has lent him multiple scientific and industry awards for several years. And for several years now, he has ranked among the most read authors on economics on the Social Science Research Network, or SSRN. In terms of recent formal accolades, the King of Spain and the Spanish government have appointed Marcos the Knight Officer of the Royal Order of Civil Merit for his services to the investment industry. That's quite something. An even greater honour than being asked to speak at the Rate & Capital inaugural event. It's really an honour to have him here today. Now, I know that his presentation is going to be of a technical nature today. It's going to be a bit of a back-to-school vibe, so I hope you've got your pens at the ready. And I will have some time after his presentation to unpack a little bit what his frameworks mean for the practitioners in the room. But Marcos, please, stage is yours.
All right, well, thank you for inviting me to be here. It's wonderful to be here in Norway. It's such a beautiful country that has so much to offer to the world. Today we're going to talk about machine learning asset allocation. In order to do that, first I need to introduce a few concepts so that we all understand what I mean by machine learning and what I mean by asset allocation. So machine learning is essentially a way of learning complex patterns in a high-dimensional space. Think of the typical matrix where you have many columns, perhaps even more columns than rows, without being specifically directed. The algorithm is going to find that pattern for us. It's not that we're trying to estimate the beta, where we already have some equation or some idea of how the x and y variables are connected. The algorithm is going to find that pattern for us. So consider this covariance matrix. There are about 5,000 corporate bonds here. And you might think, well, this is a lot of data. And yes, we can put this into an optimizer, and Markowitz will do the magic. But then we can use a hierarchical clustering algorithm, and a great insight comes through. In reality, there are about 4 bonds in this universe. You have this huge cluster that are all extremely highly correlated, those bonds, this second one, this third one, and this fourth one. And then there is a lot of independent noise, we might call it there. So essentially, there are 4 leading sources of risk here, and then some small pockets of diversification. Let me tell you a little bit about how I have used machine learning over the past 25 years. At the same time that I was managing funds for these organizations, UBS, Tudor Investment Corporation, Citadel, Guggenheim, and today at the Abu Dhabi Investment Authority, I was conducting research at a number of institutions. I'm still an affiliate of Lawrence Berkeley National Laboratory, which is the first national laboratory that was established in the US and the precursor for Los Alamos, where the Manhattan Project took place. There I did research in computational sciences, in particular how to make some algorithms more efficient that can be calculated, estimated quicker. Then at Cornell, I have developed a number of courses and theories that are taught at the master's and PhD level. I did my postdoc at Harvard. What came out of this research are a number of algorithms that are well known or used at a number of organizations. Hakon mentioned one of them before, hierarchical risk parity. Another one would be the NCO algorithm, which I will talk about today. nested cluster optimization. Perhaps you have heard of the VPN algorithm, which predicted the flash crash 2 hours before it happened, the crash of May 6, 2010. Then a number of approaches like combinatorial purge cross-validation, which is very useful for avoiding overfitting. Corrective AI, which is a new branch of AI that is, I will refer to that later. And then what is known as the false strategy theorem. This is a theory in mathematics that essentially tells you that there is no Sharpe ratio that keeps you out of trouble. You can achieve any Sharpe ratio just by backtesting, and eventually you will achieve the Sharpe ratio that you want, even though the true Sharpe ratio is 0. So that's a warning sign that there is no rule of thumb such as this strategy has a Sharpe ratio between the backtest. Certainly, it must be a profitable strategy. No, actually, it's always achievable. A Sharpe ratio of 1,000 is just a matter of computational resources. So I published a number of books, most recently one called Causal Factor Investing, where I advocate the use of causal discovery tools to try to make a number of accurate estimations of factors and risk premia. Machine learning for asset managers, which perhaps is more relevant for today's presentation. A couple of other books, Advances in Financial Machine Learning, which I believe is the first book that was published on this topic of machine learning applied to finance. I have also helped governments in a number of tasks. When the flash crash occurred in 2010, I collaborated with the SEC and the CFTC in the investigation of that phenomenon. More recently, in 2019, I was invited by the US Congress to give testimony on various aspects of AI policy. And then other engagements with governments that I should not talk about, so I just skip to the next. Current applications of financial machine learning. There is this misunderstanding, perhaps, that machine learning is about predicting prices. And I challenge that. I would say that that's perhaps the least interesting way of using machine learning. There are much better ways of using this technology for investing. In particular, portfolio construction, which is something I will speak about in the second part of this presentation, is perhaps the best application, or the one that we are going to see a benefit compared to the more established methods such as convexity optimization, Markowitz, Black-Liederman, etc. In that context, in the year 2016, David Bailey and I, we proposed a new method called hierarchical risk parity. And we don't need to go into the details of the math of how it works. I just wanted to represent this visually. When you do Markowitz optimization, you have this covariance matrix. In this case, this is a graphical representation of a covariance matrix of 50 by 50. And what this shows is that between any two assets, you need to establish a link. And that link needs to be estimated with at least two observations. In order to have an independent estimate. Now, apply this to this very small 50 by 50 covariance matrix, and you would need something like 5 years of history of daily observations in order to at least have a covariance matrix that makes sense from a mathematical perspective, meaning that you can invert it. Now, that would assume that the underlying correlation structure that you are trying to estimate has remained constant over those 5 years, which is an incredible assumption. The idea of HRP was to use the data in a smarter way. We have our 50 assets. Can we find some sort of tree structure that encapsulates the relationships between these assets, and it only requires n-1 observations, so 49 days. Instead of using 5 years of data, now you only need 2 months of data. And with 2 months of data, you can make a better assumption that these correlations have been constant over the past 2 months as opposed to 5 years. That results in Monte Carlo experiments, and this is not a backtest. just in Monte Carlo experiments, where you can very accurately estimate the benefits of this approach, this leads to gains in the Sharpe ratio of in above of 31%, meaning that you are able to model the risk in a way that out of sample in a Monte Carlo simulation, running this over millions of years of simulated data, you would observe a benefit of increasing your Sharpe ratio essentially by a third. Now, one thing is asset allocation, which answered the question, I have these assets and I'm going to give this percentage to this strategy. Another question that is typically overlooked is this strategy, should it invest at constant risk over time? Probably not. Imagine a poker player who takes $10,000 and at every hand that is given to them, he puts the $10,000 at risk. It would not make sense. No World Series player puts the same amount per hand. You need to be more adaptive. You need to size your bets. And in fact, the reason the winners of the World Series of Poker tend to be the same year after year is because what they are really good at is bet sizing. The cards that they receive should be random. And now think as an investor, the prices that you receive are essentially random. They are not under your control in that sense. You don't have the way to influence unless you are probably the Norwegian sovereign fund. Maybe you can influence a little bit prices, but typically you are a price acceptor, just like a poker player is a card acceptor. The way a poker player wins is by bet sizing. The one who sizes bets better, meaning that given these cards, they need to estimate the probability that their cards will be better than the cards of their opponent. And this is something that poker players develop intuitively. Just like billiard players, they don't solve differential equations in order to know where to hit the ball. Their brain develops this ability to find a way of hitting the ball, poker players sizing their bets. And machine learning helps us size these bets. How? Well, the short story is that if you have an algorithm that makes some forecasts, and these forecasts, they are not very accurate, perhaps they have a precision of something like 51%, but as long as there are many forecasts, you may be able to do a trade-off between the recall of the forecasts and the precision. Essentially, there is a secondary algorithm that predicts whether the primary algorithm is going to make the right decision or not. So this is a very interesting way of utilizing machine learning, and that's what some colleagues of mine decided to call corrective AI. In my original papers, I call it meta-labeling because that's more of a technical way, but perhaps their way of calling this approach is more intuitive, is corrective AI. Is the AI that tries to correct for the mistakes of another AI or the mistakes of a human. A third approach is to identify structural breaks. As Antti mentioned, correlations probably are around 0.3, we just don't know the sign. So sometimes it's positive, sometimes it's negative. Can we identify the break point? And AI happens to be very good at that. Let me give you an example of a comparison of a traditional technique like ordinary least squares and a machine learning approach, which is called ransack. Here I'm going to show you the typical risk factor approach where you have an economic factor and you have evaluation. There is, in this case, no outliers. And as you can see, as the Gauss-Markov theorem tells us, the estimate is unbiased. But as soon as you put 5% of outliers, look how wrong this estimate is. This means that there will be some stocks that we should sell that we will be buying, and some stocks that we should be buying that we will be selling. Ransack, in comparison, doesn't get fooled by these 5% outliers, or even if the outliers are 10%. As you can see, now this line is very tilted. Ransack still gives you the correct estimate. 25% outliers, which is a lot of outliers, And still, ransack doesn't get full. The algorithm is designed to produce unbiased estimates, even up to 50% outliers, at which point, what is an outlier anyway, if it is 50%, if it is more than half of the data? But it tells you the robustness and the capabilities of an algorithm. Now, many people, when they talk about machine learning and AI, they talk about ChatGPT, transformers, generative AI, and to me, this is one algorithm out of many. The reality is that there is a lot of hype on these sort of technologies, transformers, etc. But for other algorithms, ransack, random forests, boosting algorithms, and so on, these algorithms have been around for many decades. We understand them very well, how they work, and they can solve many investing problems that other traditional algorithms they are not well suited for, because financial markets are very complex. Hedging is another very important application of machine learning. There is some work that has been done by some investment banks that allows them to do what they call deep hedge. This is the use of deep neural networks to try to make some predictions about the direction of the derivatives markets. And they do so in a Greek-free, model-free way, meaning that they do not go into these very complex mathematical models that require solving stochastic differential equations, which would take a team of mathematicians perhaps months, if not years, to solve. They can do it on the fly. The solution will not be ever as accurate as the solution that some of my colleagues have done when they solve it by hand, but these algorithms can provide a solution within minutes, and even if it is not perfect, that already gives it an edge. It's better to have a suboptimal answer quickly than an optimal answer once the price has already moved. And structured data is another huge application of machine learning, perhaps one of my favorites after portfolio construction. This is the idea that you can take, for instance, news articles, Katie publishing many of them, and you can classify them based on the sentiment that they express, meaning that should a reader have access to this information, would they be more inclined to buy or sell the stock, or perhaps neutral? So that's the experiment that they are trying to emulate. And you can do that for thousands of news articles per day on a given stock, in this case Tesla, and you can see here is that when there is an imbalance towards negative news, the price will trend down for months. We're not talking about a few hours of advantage or days or weeks, even for months. And why? Because narratives spread like a virus. Just like COVID spread and it took time to reach all of us, eventually these narratives impact the price. And that can occur over many months. Conversely, when there is an imbalance towards positive news, you can see that the price trends up. And it can trend up 30, 40%. When there is a balance, but there are many positive news and many negative news, you can see that there is tremendous volatility. So again, this is another way in which you can take data that is non-numeric, can be words, can be images, can be measurements from various sensors. It can be all sorts of data, recordings that typically we would not utilize, for instance, for a Markowitz approach. And machine learning helps you translate that information into actionable insights. So to me, this is one of the great exciting areas of use of machine learning. Number 6 is feature importance. We all hate black boxes. Even if an algorithm is right, we cannot really commit capital if this prediction is not understandable. So what machine learning can do is to utilize some of the features and tell us where the predictive power is coming from. As you can see here, what we are looking at is we have a number of features. And what we do is we randomize some of the features. After randomization, the predictive power of those features that are truly predictive falls, which is an indication that there is information that can be conveyed. Then you have the detection of false investment strategies. What this means is that you can backtest a number of strategies and identify really how many different strategies you have backtested so that you can deflate the Sharpe ratio that you have optimized. So this is an application of ML that allows you to avoid overfitting, or at least not fall in love with your strategy and understand that, in fact, there is always some overfitting. So the question is not whether our quants are overfitting, but how much they have overfitted. Application number 8 is very well-known, execution. And as you know, high-frequency trading has been doing this for a long while. It consists in taking all the information from bids and asks and try to understand whether there is an informed trader. Are we going to provide liquidity to the market at a cost or at a profit? And avoid pushing the market when there is for instance, market makers are disappearing, which was the case of May 6, 2010, the flash crash. Application number 9 is another one that is very interesting. It is to automate the process of generating credit ratings and recommendations. Here, the idea is that if we are able to emulate the way that Moody's provides ratings, then we may be able to be one step ahead. So we may be able to predict when Moody's is most likely to cut the rating of a bond. And Moody's is typically, like many other rating agencies, a very thoughtful, slow process. By the time they do the rating change, the algorithm will have predicted that the rating change was going to happen, which gives you weeks of advance to build your position. This is particularly useful with the so-called falling angels. A falling angel is a bond that is BBB minus that becomes BB plus. As a result of that, insurance companies will have to drop that bond. They just cannot hold it. And imagine if, for instance, you have a bond that is a BBB minus, and you know that it's going to, very likely, is going to be cut. And all of a sudden, insurance companies, even though they love this bond, and they believe that it's a great idea to hold that bond, they will be forced, legally forced, to drop their position. And that creates huge opportunities in the market. And finally, I put it last, price prediction. I know that 99% of the papers of machine learning in finance deal with this, but I really just wanted to make the point that, yes, it's very cute and nice to look at these papers where they say, hey, I can predict prices of the S&P because I use this feature and this technology, etc. And my point is, so what? Maybe you're right, maybe your approach is completely overfit. There are so many better uses, more trustworthy, more reliable uses of machine learning in financial markets than just price prediction. Now, let's go to the first application, portfolio optimization Markowitz solution. I know that you were all waiting to look at the math because that will make it so much clearer, but I'll just go and give you the points that are really important in these formulas. So really the purpose of this equation is just to indicate to you where the results come from. This is a standard Markowitz problem. This is a problem that Markowitz, as a very young man, PhD students in Chicago, solved. And essentially, he realized that he would like to minimize the amount of risk held by a portfolio subject to obtaining a particular outcome. You could call this A bar a target return, but it could be something else. It could be what is typically called a characteristic portfolio. And this characteristic portfolio will change your position in the efficient frontier. So for instance, if you put here a fixed number, a real number, what you will obtain is the minimum variance portfolio. Now, if you have here several numbers, like expected returns, this will be the market portfolio. And then linear combinations of these portfolios will give you the efficient frontier. Now, this is known that to have an analytical answer, you need to compute your Lagrangian, solve for first order conditions, and this is what you get. Now, I want you to pay attention to this equation. What it says is that in order to estimate your optimal weights, you need to invert your covariance matrix and multiply by a vector of expected returns. And that's the problem. The problem is that in order to do that, you need to make some estimates. We do not know the true covariance matrix. We do not know the future expected returns, right? As Antti would say, we might not even know the sign, much less the leading number, much less the first decimal or the fifth decimal for that matter. So here what we are doing is we are using a covariance matrix of which we do not know much. We need to invert it. When you invert the covariance matrix with a small determinant, because the columns are correlated, this means that the determinant, which is essentially this volume of the object, the area inside your space, is magnified. And that's what Hakon said earlier. Markowitz is an error maximizer. And he's perfectly right. It is an error maximizer because what we are doing is we have a covariance matrix with what is called a high condition number, which means that the determinant is very small. And that means that the inverse covariance matrix has some very huge numbers here, some very large coefficients. And we are multiplying these very large coefficients by a number of which we know nothing, which is the expected return. So that's the problem of Markowitz. To summarize, Markowitz solution is mathematically correct as long as you know the future covariance matrix and the future vector of expected returns, which is an impossible ask. So what do we do about it? Well, we need to understand that there are two issues, two sources of instability of Markowitz. It is noise-induced instability and something that I discovered later on, another source of instability that was not known, and is signal-induced instability. Signal itself can be a source of instability. It's a bit counterintuitive, but by the end of today, you will understand perfectly well why. Noise-induced instability occurs because we have this covariance matrix that has a very high noise to signal ratio. So there is a lot of noise for the little amount of signal that we have. We can model this using random matrix theory, and there is a very important result by Marchenko and Pasteur, who were Soviet economists who around the 80s, I think 70s perhaps, they came up with a paper where they showed that the eigenvalues of the covariance matrix follow this distribution. So essentially, this is the distribution of the eigenvalues. Right? You compute your histogram of the eigenvalues of the covariance matrix, and this is what is predicted to be if the covariance matrix is random. All right? Now, what does it mean in terms of financial markets? Well, I took the covariance matrix from Barra, and I computed the eigenvalues, and guess what? About 99% of the eigenvalues fall exactly under what Marchenko and Pasteur predicted it would be. And again, these are mathematicians from the 1970s or so. They did the research in the context of nuclear energy, but their math applies. What this tells you is that the signal-to-noise ratio in finance is very, very low. Only a few eigenvalues escape what was predicted by Marchenko and Pasteur to come out of a covariance matrix. So this has huge implications for us because the smallest of these eigenvalues, is the one that is going to determine the determinant of the covariance matrix. Remember that the determinant of a covariance matrix, and I know that you remember this from linear algebra, is the product of the eigenvalues. So if you have even one eigenvalue that is small, it's going to push down the determinant, which means that it's going to make all of these coefficients of the inverse covariance matrix massive. And when you multiply that by the expected returns, of which we know nothing, you end up with signal-induced instability, meaning that if you change one of the rows of your returns matrix, that can change the inverse covariance matrix completely, and that means that your efficient frontier will look completely different. And that's just changing one day of returns. Essentially, it becomes a random number generator. What can we do about it? Well, my proposal is the following. This is noise. So since it is noise, I like canceling noise. You have your Bose headphones, and what they do is they cancel things, right? They crash one wave against another so that what remains is a flat line, you don't hear it. And here we have all of this noise, let's cancel it. Let's just average. And in that way, your mean eigenvalue will be here, not here, it will be here. Now, it makes a huge difference to have an eigenvalue of 0.01 versus, let's say, 0.1. All of a sudden, this covariance matrix is not ill-conditioned anymore. And it means that your solution will be much more robust. And that's essentially what the constant residual eigenvalue method does. Essentially, it takes all of these eigenvalues that are almost zero, right? This is in log scale, so this is a very, very small number. And there is a huge difference between being here or being here. We're going to replace all of these small numbers by their mean. That's what I call noise cancellation. It's denoising, right? And all of a sudden now you will have efficient frontier estimates that are much more robust. We can do this, we can reach this conclusion through a Monte Carlo experiment. So what we can do is we create a covariance matrix, which is the ground truth. We take this covariance matrix as given. Let's say that this is the historical covariance matrix. And now what we are going to do is we're going to take this covariance matrix, we apply Cholesky, we generate some random samples, and these random samples will have this covariance structure. We do that for a sample, let's say 1,000, I don't know, a year of data, perhaps, or 2 years of data, and we can do this many times. We can do this for 1,000 times, let's say, right? So we're going to create 1,000 alternative scenarios where each scenario is characterized by a random matrix that we have randomly drawn from this ground truth that we estimated. So the question here is, can we recover the true covariance matrix from these samples that we are generating, these 1,000 samples? And the method that is able to recover the ground truth from these drawn samples is the one that is more robust. It's the one that we would trust today because we can see that on simulated data, it tends to be a better estimator, right? So that's the idea of a Monte Carlo experiment. And what the Monte Carlo shows is that there are some incredible gains when you do that. When you utilize denoising on estimating the mean variance portfolio, right, the left edge of the efficient frontier, you obtain a reduction of around 60% in the mean square error, right? Compared to what you would attain with Ledois-Wolf, 30%. Why is it that denoising is twice as better as Ledois-Wolf? And Ledois-Wolf is a wonderful tool. I'm a friend of Michael Wolff, so I definitely appreciate his work. But why is denoising better in this context? In this context, it is better because what we are shrinking is noise. We are not shrinking the entire covariance matrix. Let me go back to make this case. Rather than shrinking the entire covariance matrix, we're going to shrink this alone. We shrink noise only, not signal. Who wants to shrink the signal? We want to amplify the signal, right? So this is why. We understand well why this algorithm performs better. It performs better because it does what it's supposed to do. When you apply that to the maximum Sharpe ratio portfolio, the M portfolio in the efficient frontier, then the gain is even better. It's a 94% reduction in the mean square error. Now, I don't know you, but I don't know many cases in investing where you have an approach that produces an improvement of 94% compared to the traditional method, Markowitz, right? So my question is, why would not, is not whether you should do denoising. The question is, why would you not do denoising? Why wouldn't you cancel off this noise that is present in the covariance matrix? Now, I said that there are two sources of instabilities in your Markowitz optimization. One is noise, the other one is signal. You could say, but how is it possible that signal is a source of instability? Well, let me explain you why. Suppose the smallest possible covariance matrix, 2 by 2, and if it works for a 2 by 2 case, imagine if we are dealing with 1,000 by 1,000. You do your eigenvector, eigenvalue decomposition. This is what you obtain, right? You have your rho here. Of course, this is a correlation matrix. And the diagonal, you have your ones. And this is what you get, right? Your eigenvalue matrix has a 1 plus rho and a 1 minus rho. Now, when rho is 0, this is the ideal case. This is the case where Markowitz works very well, right? You have a correlation matrix where essentially it is 1, 1, 0, 0. There is no correlation between the assets. There is no multicollinearity. You will be able to invert this covariance matrix very well. The condition number will be very small. However, as you increase the correlation, which is the case in financial markets, right? Stocks are correlated at the 0.8 correlation or so, right? With each other. Now, when you do that, as rho increases, what will happen is that one eigenvalue will prevail over the other. One eigenvalue becomes smaller and smaller and smaller. And now the determinant is the product of these two eigenvalues. So the determinant will be 1 minus rho squared. So if rho is very high, like 0.8, all of a sudden, your determinant becomes very, very small. And now, the inverse covariance matrix is 1 over the determinant multiplied by the matrix of coadjuncts. And what will end up happening is that signal itself will be a source of instability. Remember that when I talk about noise-induced instability, I refer to having small samples, right? The source of the noise was really that we have very few observations. Let me show you in particular in the slide. You have the Marchenko-Pastor distribution, and T is the number of observations. As N and T, as N becomes very close to T, that's when this left side of the distribution becomes very close to 0. That's the source of instability. The source of instability is connected to the ratio of observations relative to the number of columns. So this is why when you have noise-induced instability, this is a problem of small samples. When you have signal-induced instability, it is not a problem of small samples. T is nowhere here. It has all to do with the signal itself. The signal itself is a source of instability. This is what I call Markowitz's course. Essentially, Markowitz model, not the person, he fails us when we need it most. Whenever you have correlation that is different than 0, the condition number will go up, your covariance matrix will be ill-conditioned, the inverse covariance matrix will have some huge numbers that you're multiplying by a vector of guesses. This is the vector of expected returns. So what is the solution? The solution is to break the problem into parts. We have a covariance matrix. We can estimate some clusters in this covariance matrix and then solve the problem for each cluster. And that goes back to the first slide I showed you, where we can use hierarchical clustering to break down the problem and understand that really we are dealing with these 4 bonds, not 1,000 bonds. So the NCO algorithm, what it does is it will apply Markowitz to the blocks that we have identified as being very highly correlated. This contains the spread of the signal-induced instability. So there will be some instability in the cost to the signal, but it is concentrated in this block. It doesn't allow to spread to the entire covariance matrix. So as a result, what you obtain is that this is the algorithm. You have your input mu and v. You can do the denoising, and then you partition the problem into sub-problems. Now you know that you need to apply Markowitz here, here, and here. And this allows you to reduce the space from n, a number n, to number k of clusters. And then you can optimize for a second round on Markowitz again. When you do that, again, we can run some Monte Carlo experiments. What you obtain is, again, massive gains on top of the gains that you obtain from denoising of the covariance matrix. In the case of the minimum variance portfolio, you obtain a 47% reduction in the mean square error. In the case of the maximum Sharpe ratio, you obtain a 55% reduction in the mean square error. Again, massive gains. We're not talking here about improving the Sharpe ratio by a little. These are huge improvements in Monte Carlo experiments. Now, let me tell you another little secret, and it is that we all got diversification wrong. We are diversifying across assets, but we are not diversifying across methods. Do you realize that when we use Markowitz, which is predicated on the idea of diversification, we are all concentrated on the Markowitz solution because we are applying the solution that Markowitz gave us. Now, that's a single point of failure right there. So as we were looking for diversification, we were doing the opposite. We were concentrating on the solutions that Markowitz gave us, which, as we discussed, are not even robust. So the idea here is that do not apply a single optimizer. Do not apply NCO, which I advocated for. Do not apply for NCO. Do not apply only HRP. Do not apply only Markowitz. Apply all of them. Take your 20 favorite optimization algorithms and then run a Monte Carlo experiment similar to the one I ran before and let the algorithm find for you what is the optimal allocation to the allocators, right? Each allocator gives an allocation to assets, but the second level allocation gives an allocation to the allocators. And that's essentially what in machine learning is called a bagging algorithm. It's an algorithm where essentially you have some low-quality predictors, but the combination of all of these low-quality predictions is a very good prediction. You may know it also as ensembling methods. The idea, again, is you have some inputs, a mu and a sigma. This is your best guess. And what we will do is we will draw some random covariance matrices, some vectors mu from this data generating process. We will compute some allocations for each of these draws. And then what we will do is we will repeat this millions of times until we understand, given this data structure, what is the optimal combination of allocators. And again, it is based on this particular correlation structure that you have today. This does not need to be based on a historical covariance matrix. It could be based on the predictions that Antti gave you. You have, but the important is that given this correlation structure, what is the optimal allocation? Or perhaps you just decide not to apply this A2A algorithm. What you may want to do is just do an equal allocation to the allocators. Either way, it's going to be much more diversifying than using one diversifier. So this would be the algorithm that you would follow for that. You have all of these methods, you apply them, NCO would be one of these methods, and now you compute an allocation, you repeat millions of times, and you estimate what percentage of times the algorithm gave you the right answer. The right answer that you know from the ground truth. Essentially, this is not a backtest, it's a Monte Carlo experiment. What we are assessing are the fundamental mathematical properties of these optimizers, right? If I don't really care in this context about a historical backtest. Historical backtest can be overfitted very easily. Here, the idea is, what is the combination of allocators that allows us to obtain a solution that is robust, that essentially that works as advertised? Okay, final remarks. I have 1.5 minutes. What makes machine learning solutions better than Markowitz? Well, it comes down to the following. Markowitz does not deal with noise-induced instability, does not deal with signal-induced instability. It's a myopic optimization, no path dependencies, is one shot into the future. They assume perfect knowledge. To me, this is really a very bad assumption. We don't know the inputs, and it's garbage in, garbage out. And it's a single point of failure. It's not even a way of achieving diversification. If you want diversification, please do not use Markowitz. It's not a diversifier, it's a concentrator. You see that many solutions will be zero, in fact. It concentrates on a few assets. In contrast, machine learning solutions are robust to noise and signal instabilities. They can be designed to solve multi-period goals. They do not assume perfect knowledge. They avoid single point of failure. Now, let me be clear, machine learning is no panacea. They don't solve every problem. They are better than traditional techniques, but they are not the best, and they cannot replace human insight. They cannot replace our knowledge of the industry, etc. If I were to give you a recommendation, the next time that a quant provides to your portfolio, is ask these questions. Have you control for backtest overfitting? 99% of quants, they do not know how to answer this question, and it's troubling. They need to use techniques like multiple testing adjustment, sensitivity analysis. They need to apply an embargo on the data so that when they did their analysis, they didn't have access to the full extent of the data. So your organization needs to control for whether people had access to the embargo and how many trials were involved in their discovery. Number two, what is the causal mechanism responsible for this anomaly? We don't like black box predictions. We need to understand where the forecasting power comes from. We need to take into account counterfactual reasoning. It's not so much about what happened in history, but what will happen in the future. We need to prepare for the next black swan. And number three, is this an ensemble method? Is this a method that utilizes many different approaches combined, like A to A? Right? We do not want a single point of failure. We want to apply bugging, boosting, stacking, meta-labeling, you name it, but there is no machine learning method that is going to keep you out of trouble. But there are many machine learning models that you can use in parallel in order to reach a solution. And there are very good reasons why ensemble methods will typically give you the best solution that you can get. And with that, I stop. Thank you very much.
Thank you so much for that. Cameron, who's sitting behind me, was saying "wow" through half of it. So you've definitely got him on board. I mean, when we're thinking about these sorts of frameworks, who are they most applicable to? What kind of professional investors can and should be using these sorts of techniques and thinking about this stuff?
All of them. The idea here is that mathematics and statistics has changed a lot over the past 200 years. Regression analysis is not a new technique. It's a technique that Gauss knew of. And in fact, it's interesting that Gauss, even though he used ordinary least squares in his papers, we know that because the estimates that he obtains are the estimates from OLS, he never thought that it was publication worthy. So he never wrote a paper on, for him it was obvious, why would I publish this? My point is that over the past 200 years, methods have evolved a lot. And today, machine learning methods are robust. They can work on small samples. They deal with all of these issues, and everybody should be familiar with them. In the end, it's not really about math. You can use machine learning just like you use your car. You do not need to be a mechanic or a technician to drive your car, but you need to learn to drive the car. You need to understand what are these levers for and what are the problems of doing this or that. And the same with machine learning. You do not need to become a developer. You don't need to become a mathematician. You need to learn to coexist and use these methods as your co-pilot.
And use it as like an early warning system. You don't have to act on every signal, right? It's just to be that kind of systematic warning system.
That's right. That's right. You need to understand what these algorithms are good at. They will give you some insights into your data. By the way, when the flash crash occurred and our systems flattened the position 2 hours before the flash crash, we didn't know why, but we were a systematic organization, so we just stay put. And then the market collapses and the algorithm starts to buy. And we didn't cause the crash. We caused we helped in the rebound. These algorithms are very good at finding things that you could not even imagine because the flash crash had never occurred before. So
what was that moment like for you when the machine's telling you one thing and your instinct is saying, I don't know about this?
Right. So this is why I don't use black boxes.
Yeah.
Right? So I apply machine learning, but there must be a theory behind it. In this case, our theory was market microstructure. So there is a market microstructure theory that predicted that in the presence of very serially correlated order flow imbalance, market makers will disappear. So it never happened, the flash crash, but the theory predicted that this thing that has never happened could potentially happen. So the day that the order flow imbalance became very imbalanced, all of a sudden, that was the black swan occurring. We trust the theory, it makes sense. The portfolio goes flat. We don't have any position. The market collapses 2 hours later, and then the algorithm wants to buy. And then a week later, we received the call from the SEC asking, what did you know?
Yes.
And at first, we thought that it was a bit worrisome to receive a call, what did you know? Well, what we knew is market microstructure theory, and we just are a systematic organization, and we follow the model. So my point here is that, yes, you need to utilize these methods in a responsible way. Do not use them as some sort of oracle. Do not use them as a black box. Understand what they are for, and never take your quant's word for it. Run experiments, challenge them, avoid that there is make sure that there is no overfitting, make sure that these are ensemble methods, and then they are safe to be used.
Yeah, I enjoyed your sort of cheat sheet on questions to ask quants when they come knocking. I mean, thinking on that point about microstructure, are there more potential risks embedded in microstructure now, given that liquidity has dried up somewhat since the GFC because of the regulatory changes we were talking about in the previous session? Is the world a bit more of a dangerous place in terms of liquidity just suddenly disappearing in moments of stress?
Yes, that's a very interesting question. Market makers develop their models based on market microstructure theory. So in a sense, it's a self-fulfilling theory. The theory itself doesn't need to be correct about their underlying nature. Then it needs to be correct about who is using them. As long as market makers utilize market microstructure theory whenever they place bids and asks, this tells you that developing models that use that give you an edge because they essentially allow you to predict what the market maker is going to do and when there could be a liquidity crisis. So it truly makes sense to develop machine learning models that are backed by a theory.
Yep. Are machine learning models at a point where they are cost effective for a broad community of investors?
Yes, yes. Think of ChatGPT, generative models. Of course, they are very expensive. But I mentioned one of them, ChatGPT, when I discuss sentiment extraction. But all of the other methods that I describe, they are methods that are, some of them 5 years old, some 10, some 20 years old. They're not 200 years old, like regression analysis. They are modern, but they are, you can't run them in your laptop. So what this tells you is that, yes, definitely, you can use AI and machine learning. There are many algorithms that are well equipped to solving your problems.
Yeah, yeah. But what are the most common mistakes that you see with people?
Yep. To me, the most common mistake is to go for price prediction.
Right.
To me, it's the wrong question to ask an algorithm. we just don't have enough insight to predict a price. But there are so many other problems that we need to solve as investors for which machine learning is very well equipped. We discussed today one of them, bet sizing. I could give another talk about that. And another talk, structural breaks. Now, if you are able to understand when there is a structural break, you can use that to delever your portfolio. So it's not even a matter of making the prediction for the next price, but you know when you need to take your chips off the table and say, you know, I call it a night. It was a lot of fun, guys, and I'll see you in the next one. So these are methods that perhaps they are not predicting prices, but they predict when you need to delever.
Yeah, yeah. I think we've got time for maybe a couple of questions. Anyone would like to raise a hand? Don't be shy. Oh, the worst thing has happened. Anti's got a question.
I love it.
Well, it's a little related to what you were just talking about. You didn't mention much in your presentation computational efficiency, and maybe we don't need too much of that, but it has improved, and so what good is it for, and what's
Yes, very good. I'm a big believer in bugging algorithms. That's what stands for bootstrap aggregation. These are algorithms that allow you to parallelize tasks. So each of these algorithms can be solved very efficiently. Even in a laptop, in a matter of seconds, you will get an answer. Now, this algorithm itself is not going to be very accurate, but 10,000 of them running in parallel, they are going to be very accurate. This is something that is affordable. You don't need to have a supercomputing cluster. You don't need to put a lot of money to work. This answer is going to be robust and much more efficient than, for instance, just using Markowitz and implementing a concentrated solution.
Lovely. Thank you, Antti. Any other questions? Don't be shy. Håkon.
Yes, in practice, how many quant analysts would you need in a team to implement these methods efficiently? Can one person do this, or do you need a whole organization?
I would say you need two. One to do it and another one to challenge him. Perhaps if you read the first chapter of Advances in Financial Machine Learning, I described there an assembly line. And I created this figure that was not common at that time in the investment industry, and that is the testing vertical. This is the vertical that plays the role of a peer reviewer in a journal. So you have a researcher who is in love with their theory, they truly believe in the theory, but then you need another researcher who has not been involved in the research and begins to ask questions and bring a lot of criticism. And as a result, what you will get is essentially a better paper. You see that in a journal. You cannot imagine the papers that you get into a journal and how the peer review process improves them dramatically. And you need the same figure in every organization, even in a small team. You need people who were not involved in the research project, who do not believe in the idea. They are neutral, they're going to be fair, and they are going to poke holes into this idea. So to me, this adds tremendous value and will avoid situations where you end up overfitting to a very large extent and relying on single points of failure.
Always get someone who always says no. Right.
You have it in your, when you have a column, I'm sure you receive complaints from the editor. Why did you say this?
It's mostly the readers, but yeah.
Oh, yeah.
But same difference, yeah. Yep. Lovely. We're going to have to wrap up there. Marcus, thank you so much.
Thank you so much.
Extraordinary.